Hello and welcome to my presentation about 3D rapid mapping on mobile devices. My name is Clemens. I'm a master student of the University of Applied Sciences in Salzburg for computer science, and I'm also part working for the geoinformatics department at the University of Salzburg. This summer, the Department of Geoinformatics announced a project and chose 4 students out of the applications. One of them was me, and we were supervised by Dr. Bernd Resch and Professor Blaschke. The intention of this project was that there are multiple solutions which perform structure for motion or hard computational algorithms on PCs or on servers. And we think that it's possible also to do this on standard smartphones in real time. The overall application would be that we have an application to navigate through a building by simply taking pictures of a room. Okay, so at the start we did a little research phase, and I just want to point out 2 publications. The first one is a continuation of a publication of 2011 and is continued 2014. They have a similar project than us. They take pictures of a room, then send them to a server, to an external server. This server extracts the features of the images and compares them with features in a database on the server. At the end, the smartphone pulls the request to get the location where it stands. And so we think this could be also totally done on the smartphone itself. The other publication I want to mention is announced in 2015. There the scientists just place an objective on the table, move the camera around, and instantly get a 3D model out of from the object. This is completely done on the smartphone, and I want to mention that they use the resolution for the images 320 times 240, which is extremely small. So at the beginning of of our project, we defined what could be our workflow. First, we take some images, then we process structure for motion. Shortly, a description of structure for motion. This is how you can get a 3D model out of 2D images, which is coupled with the local motion. Then we have to do point cloud processing, and we also do the visualization of the point cloud, but this is just a byproduct as we want to get the significant points out of it and don't want to visualize the rooms. At the end, because the project is still in progress, we would like to implement a fingerprinting algorithm and then have indoor positioning. So at the start we have an evaluation phase and looked at different libraries and softwares to find the best solution for us. One of our major criteria was that they have to be open source, that we can reprogram parts of it and can hands on the code. And half of them were open source, and one of them is in brackets, the libviso2, because they state that they are open source, but they never send us any code, so in our definition they are not open source. Then we defined if it's a library or software. A library would be preferable, of course, but when we have an open source software, we could also extract the models which perform structure for motion. And at the end, we wanted to know what's the organization behind those projects. Then we take a closer look to certain candidates and define other criteria like the dependencies, input-output, documentation, API, features, and so on. And at the end, we decided to take OpenMVG. OpenMVG is written in C++. It is a collection of tiny open source libraries, so we don't have to use all of them, and this is very helpful because we want to keep the data storage as minimized as possible. It has integrated an incremental and a global structure for motion pipeline, and the author of OpenMVG was very enthusiastic and wanted to help us, and his name is Pierre Moulin. But we had some major challenges to face, namely OpenMVG was just built for Linux and Windows currently, and we would like to use it on an Android smartphone. Therefore, we had to build OpenMVG for Android, and as another challenge is that they have a lot of C++ standard functions, they are not fully compatible with the Android operating system. And the last challenge would be that it also has a lot of dependencies, like Eigen, the series solver, and other, and this could always be a spot which could be a problem in the end. But we succeeded in making OpenMVG usable for Android and solved the stated challenges and successfully performed parts of the structure for motion pipeline. Then, meanwhile, we tested also the OpenMVG library to find the best solutions to use it. I would like, this is a short GIF. These were the pictures we have taken for the experiment. It's a kind of a messy table with, for example, the bottle on it, and we tried to visualize it in a point cloud. Therefore, we use the global structure for motion pipeline, and I would like to shortly describe it to you. We take some images, extract the features out of the images, then then match the features of the images and estimate the camera poses from which angle the pictures were taken. At the end, we perform the SIFT algorithm and create the point cloud. And at the end, we do bundle adjustment to reduce the residual errors. And as you can see, at the end, we get a point cloud. So these were our first results from our experiments. There were the setting normal. You can see the bottle and the monitor as well as the desk. And when we set the setting to high, the floor gets really high density, and as well as the cupboard besides. And it has another setting called ultra, and there the density of the point cloud is extremely high, but it also takes a long time. This is illustrated in the next graphs I will to show you, and to find this, we have to find the best parameters for the resolution and the number of images to keep the computation time as low as possible. Therefore, we use the windowing method, as we take a picture of a room and then just move 30% up, and then we have an overlap of 60% to the next image. This was our output of the first experience when we changed the number of images and as well as the settings. There you can see that the y-axis at the top is in minutes, and the bottom graphs are in number of points, the y-axis. And the x-axis is always the number of images. You can see that it's is an increasing slope like an exponential function in the minutes, and it's very linear when you get the number of points. We think that in 10 minutes you can see that the slope of the high setting is as well very low, and you get already a large number of points, about 2,000 points. Therefore, we used it in the next experiments with more resolutions, and we wanted to see if we get the same result in different sceneries. As you can see in the image in the graph right at the top, there we use the resolution 800 times 600, and sometimes we get almost 0 points when we use the low setting, but when we take more images, it's always more computation time. Therefore, we wanted to emphasize the high resolution as the computation time is still very low, and we get a lot of points, and the variation is also very high. So this has currently been done. We want to combine the app from structure for motion and the visualization together because we visualized it as well in an app. We would like to do a point cloud merging if it's necessary and have to reduce the number of points if needed to keep the data storage low. And in the end, we want to implement the fingerprinting algorithm to perform indoor positioning. So in my last slide, we have some open questions, and I would like to hear maybe some experiences or solutions from you. The first one would be, what would be the best point cloud reduction algorithm? Do you have any experience with fingerprinting algorithm for indoor navigation? Is probably served the better solution as SIFT in the mobile device world? And how we can increase the algorithm performance. Otherwise, we can talk as well in the break. Thank you for your attention.
Yeah, thanks. I think for the first point, maybe we would have someone from the autonomous car data collection team here. I don't know. Anyone here? No. I think the second point is, I mean, we have an indoor topic afterwards. Maybe it would also smart to connect then with these guys. Bernd from indoors is also, I think, there. Where is he? Ah, here. Okay. Maybe you have some suggestions already? Okay. Okay. Yeah, I think it's also great. Well, anyone else has some opinion? Ah, yeah, there was a question. Sorry.
That wasn't a question, it was a comment to your questions there. So I was involved in research about indoor localization in different institutions in Germany and in other countries. And we investigated if we combine different algorithms for indoor navigation, then we could achieve, increase the probability of recognition dramatically. And then we investigated how many of these technologies we should combine. And the surprising result was that if we combine two different technologies that are kind of have the principles, the physical principles behind are kind of orthogonal to each other, so not two similar methods, but two completely different ones, then you significantly increase the recognition rate of where you are in the upper 90%. So let's say something spatial like Wi-Fi fingerprinting, if you combine that with being recognized at certain points, like seeing a visual marker or passing a RFID gate or so, then these are two completely different principles, and combining these dramatically increases your recognition rate.
Was it helpful?
Yeah, of course, yeah. Maybe
Okay.
we can talk in a break as well.
Okay. Any other question, comment, whatever? Yeah, then thanks again for the talk.